And we have the pleasure to have as a speaker of today, Nikolaus HERMANSPHAN. I'm sorry if I pronounce it in the wrong way. So Klaus has studied physics at Mainz University, where he gained a doctoral degree for his work on the magnetic moment of hydrogen-like carbon. He was working at a fairly low level of accuracy, ppm range, and even lower later. And all of this contributed to the value for the electron mass in atomic units. After that, he continued research in atomic physics at the Harvard University as a postdoc, where he worked further on the fine structure in helium, and then was confronting to the real world. So it means world with real radiation and radioactivity, and that's at the National Radiation Laboratory in New Zealand, which now has another name. And while the focus of his work was on environmental radioactivity measurement in the ISO 17025 accredited laboratory, it was also introduced into all the aspects of the CTBT treaty verification. And of course, with these links at the end, straightforward, he go to a position as a CTBTO in 2018, where he's now responsible for the radionuclide team of the engineering and development section. So the section tasks include oversight of technology development, including the acceptance of new measurement system. As with all measurement services, processes for calibration quality assurance are integral to ensure customer trust in results, but you will have more details in a more understandable way by Nikolaus himself. So please, Nikolaus, I'm very pleased to let the floor to you.
Thank you very much. Now, it's entitled Metrology in Support of the Comprehensive Nuclear Test Ban Treaty. In fact, it will be very little about metrology, and I will try to explain a lot about our work. But before I start, the disclaimer: this is not an official presentation of my organization. It's my personal view on the matter, if anyone should ask. So the idea is to explain a little bit about our treaty, to then move into how this treaty is verified. That's done with the international monitoring system, so I will explain that. That has several technologies in addition to the radionuclide monitoring. So I'll go into a little bit of the detail of those other technologies before I explain radionuclide monitoring. We do gamma spectrometry on aerosols, and we do noble gas measurements, in particular like xenon. So treaty, and everyone loves treaty wording, so I'll put a slide in here. It is actually quite simple. It says that each state party undertakes not to carry out any nuclear weapon test explosion. So it's not only test explosions are banned, but any type of nuclear explosion. And the second paragraph basically just ensures that there is no loophole. It also refrain the state parties that sign the treaty also undertake to refrain from causing, encouraging, or participating in any type of nuclear test explosion or nuclear explosion. So not too difficult, really. Of course, the treaty goes on further with, from there, but on the basis, it just bans any explosion. And the treaty is almost universal. We have 187 states that have signed the treaty, of which 178 have ratified it. It's not yet in force because of the way it was designed, but in the meantime, it has been effective in stopping nuclear tests, with the exception of North Korea. It does prevent nuclear proliferation, both horizontally, vertically. So in one, it makes it harder for new weapon states to gain the expertise to build nuclear weapons, and it makes it harder for existing nuclear weapon states to develop new types of weapons. Because at some point, you will need to do some actual testing to confirm that it works. With that, it's an important step to a world without nuclear weapons. The treaty itself, our treaty does not ban, stop states from owning nuclear weapons, but they just can't do anything with them. Now, it's fine to have this treaty, and I think we all agree it's a good thing to have, but you need to also verify that each state complies with the treaty. And this is the treaty verification, and there are several building stones to that. One is you need, of course, it's good to have data. So we have an international monitoring system, including 337 facilities. I'll show a map in a moment. And with 4 different technologies that were identified at the time the treaty was negotiated. And that's a very important block in this. Of course, then the data may need to want to discuss further. There's a step of consultation and clarification. The states should talk to each other. Once the treaty enters into force, there will be the option of conducting on-site inspections. So with an international team, there wouldn't be wouldn't be our staff. It would be inspectors from different states that travel to a site where a suspected nuclear test has occurred and conduct inspections, measurements, essentially to confirm that there was no nuclear test, because the state to be inspected needs to agree. And then there's confidence building measures. For example, states may announce large chemical explosions, like in mining industry, that helps to prevent misinterpretations, but also even allows for the calibration of seismic instrumentation. So this is what our monitoring system looks like. I'm not going to go into the details here too much, but just want to point out, so we have these 37 facilities. The different symbols indicate different technologies, but more importantly, the colors indicate the status. So anything in green is a system that's certified. If it's operational, it contributes to treaty verification. We're receiving the data. All the other colors indicate that there's still work to do, but we're about 90% complete. So, as I mentioned, the 4 different technologies, and there's the 3 what we call waveform technologies: seismic, hydroacoustic, and infrasound, where we're basically listening for the explosions. And this is very important. This data is available instantaneously, basically, whereas radionuclide data takes time. I will go into that later, but the important aspect of radionuclide measurements is that by looking at particularly isotopic ratios, we can possibly identify that there was really a nuclear test and not a civil event. And for that, the radionuclide technology has a special status. Well, that's our opinion. So, of course, we need to transmit the data and process the data. So there's communications infrastructure that supports it, a data center. We have so our network of stations. The communication goes partially through satellite network. We don't own the satellites. We have a contract with a provider for bandwidth. Nowadays, of course, we have usually as a primary connection, a VPN through a normal internet, which is much faster. But the satellite communication is there as a very robust backup. Here in Vienna, we have an international data center where we receive the data, store the data, process the data, and make it available, and our what we call products, information for the state parties to evaluate. It is with the state parties, with the national data centers that make a decision whether they believe a nuclear test was conducted or not. But that's as far as I want to go into that. First technology to look into a little bit of detail is seismic stations. So this is the sub-network, seismic stations only. There's two types, primary and auxiliary. That's in two sensors. Primary one is the primary stations we look at primarily when we do the data analysis, and the auxiliary ones are only used when the data needs to be refined further, but also in a sense that the primary seismic stations we actually maintain. The auxiliary seismic stations are part of national networks. We just get access to the data. Again, yeah, green color means those stations are active and contributing. Now, seismic technology has long been established, and of course it's used for earthquake monitoring. Now, I'm not a geologist, but so basically there's a slight difference between earthquakes or an explosion. Of course, just from a simple point of view, the earthquake is generated by tectonic plates moving against each other, whereas the explosion is an explosion that generates a different type of wave. That generates a slightly different signal, and also it has a different travel time from the source to the sensor. And in the example, we have here three signals, two from nuclear explosions from 1992, 93, and one from an earthquake from the same period, so the same sensor. And obviously the explosions start with a big signal and then taper off with the earthquake. Already looks quite different. But I'm not an expert, so it's pretty much all I can say about this. So in terms of metrology needs, for this technology, it's of course well established. So the processes exist pretty much. There's just for the very low frequency range, there are currently no CMCs, but that's also work in progress. Then there's hydroacoustic stations, so basically microphones in the ocean, or listening for sound waves generated in the ocean. And actually two different types. There's actually hydroacoustic stations and so-called T-phase stations, which are seismometers situated on a small island. And in the case of the hydrophones, they're based on the fact that in the ocean you have depth gradients with salinity and temperature, and they both influence the speed of sound. And you end up with having like a waveguide at a certain depth that differs from location to location, but it's usually a few hundred meters of depth. So if you place a microphone in there, you can listen very far, particularly with low frequency, if you're listening to low frequencies. That means, though, you have a fairly complicated and expensive setup where, of course, you still need an island to place your electronics and your communications, and then you need a long cable to place with microphones in this channel. And you want you have 3 microphones. That's not just for redundancy, but also to have directionality. For the T-phase stations, as I mentioned, there's a seismometer on a small island. The sound waves will couple into the ground, either further away or close to the island, and then are picked up by the seismometer. This just shows the coverage. In fact, there's only this 11 stations, or 6, in this case, 6 hydrophone stations, and that they actually really cover the whole oceans pretty much. Yeah, just some pictures to show that it's fairly intensive effort to put these stations into the ocean. If you're keen, there's some YouTube videos to watch. And of course, we're not only picking up explosions, all kinds of noise, sound waves, including mammals, marine mammals. I'm not going to play these for this meeting, but there's also online, you can find some of these. In addition, we can pick up other sound waves. I believe data from our network was used, for example, for the Argentinian submarine accident to help identifying the location of the accident. There actually, for this hydroacoustic monitoring, there is no calibration capability at this point. So that there's definitely some assistance required. Next technology to discuss is infrasound. And so listening again for low frequency waves that travel long distances. The total of 60 stations planned, of which 90% have been installed. So infrasound, we're looking at sub-hertz to 4 hertz frequency range, because this is the frequency range that can travel long distances and covers the important sources like explosions. Of course, we're not only picking up explosions, there's also supersonic aircrafts, rocket launches, volcanic eruptions, even aurora can be heard. For the infrasound, stations are all arrays, and they're sort of set up to have directionality. Essentially, they're just microbarometers, but hooked up to a large number of inputs. So you can see the star-like arrangements. They're just individual inlets that combine to a single entry port. That's then there's a single barometer sitting in this white box in the middle of the picture. Ideally, you want to have a fairly regular arrangement of these nodes and to get a easy way to reconstruct direction, but that's not always possible because we're looking at fairly large kilometer-sized arrays, and just because of the lay of the land, you end up with slightly misshapen arrangements. Also, I mean, one issue with these measurements is noise, particularly wind noise. So ideally, you'd like to go to a forest to cut down wind. Of course, forests also then are challenging because of not always able to clear all the trees that are in the way. So installation becomes complicated. And of course, there are environments where there are no forests, and you just have to live with wind as it is. For these barometers, there is well-established calibration capability. There, the need was more from our side in intercomparisons and comparisons to other institutes to establish the validity of our calibration efforts. With that, we come to the more interesting part, which is the radionuclide stations. As I mentioned, the radionuclide technology is only of the four where we can clearly distinguish between a nuclear test and a chemical explosion, provided we can pick up the plume. In the scenario of an above-ground nuclear explosion, that would result in a large release of particulates, so aerosols, as well as noble gas isotopes, and at the level of Fukushima or so would be no problem of picking up this amount of radioactivity. Above ground explosions cannot be hidden. We will detect them. Underground explosions can be sealed off, and to the point where there's no release from aerosols. That can go wrong, like the example of the Bainbury test. The picture there shows a US test in the 1970, where that was meant to be sealed off, but somewhat failed. But even a sealed underground explosion can release some radioactivity into the environment. The explosion itself creates cavity. The explosion may shatter some of the rocks, create cracks, and the cavity itself at some point can collapse, which again leads to some disturbance and may lead to release of aerosols even, but of course the noble gases have a higher probability of escape. So the noble gas detection is an important part of our measurement network. When the network was designed, the idea was to have, as a design goal, a 90% detection probability to detect a 1 kiloton nuclear explosion within 14 days anywhere on the globe. Now, 1 kiloton was chosen as a fairly small nuclear device, actually not that easy to make. The uranium devices used in Hiroshima was never tested. It's just two lumps of uranium shot at each other. That was around 10-15 kilotons. So my understanding, to get a 1 kiloton explosion or something smaller is actually not that easy to do. So the 1 kiloton is a reasonable lower limit. 14 days, we need to have a time limit because of course the radioisotopes need to travel from the source location to one of our stations. That takes time. Then you can work out from a 1 kiloton explosion, you get 10 to the 15 or 10 to the 16 becquerels of key nuclides. In our case, so for particulates, that's barium-140, and for xenon, we're looking at xenon-133. Then you can make an assumption on how much activity is released from the underground nuclear explosion. And those estimates are on 0.1 to 1%, which means that you need to detect a release of 10 to the 13 becquerels anywhere on the globe. 10 to the 13 becquerels sounds like a lot, but distributes quickly once released. So based on this 10 to the 13 becquerels release, the decision was made to build up this network of 80 particulate stations, or 80 radionuclide stations, and it was decided that 40 of those should also have the noble gas detection capability. In the future, this may be increased, but at this point, the decision is to have 40. And then from this reasoning, we have a sensitivity requirement of 10 microbecquerels per cubic meter for barium-140 and around 1 millibecquerel per cubic meter for xenon-133. So this is what the radionuclide network looks like now. Again, green color is active, about 90%, 73 stations have been certified. And this network is supported by radionuclide laboratories, 16 laboratories that support the network by conducting QC measurements and repeating a measurement of a sample that was measured at a station on a routine basis. And for if we have suspicious samples, we can split them and send them to two different laboratories for repeat analysis. This is what it looks like as an example, station in Darwin, Australia. This is a manual station. We have the air samplers. Of course, we need a satellite for the communication, and somewhere building to place your detector. And this station also has a noble gas system, which is not so much visible on the outside. So for particulate stations, we have different designs. On one hand is the manual stations, where operator has to come every day to change the filter. We operate on a 24-hour cycle. We also have two types of automated systems. The photos are a bit old, but there's on the middle top, it's called a Cinderella, it's like a robot-based automated system. And then on the right-hand side, the RASA, the US type automated sampler and analyzer. They're all based on gamma spectrometry on germanium detectors. So the general scheme, we have, of course, sampling, where we collect the samples, either done by filtering for the aerosols or the gas collection for noble gas. Then the sample is counted, analyzed, and data sent to Vienna, to the data center for processing. As part of the processing, there's atmospheric modeling, backwards calculation conducted to see where possible source locations may be. I will also show another example in a moment. For the particulate sampling, the process works on a 24-hour cycles, 24-hour sampling. We have a decay period to reduce the radon count rates, gives us more sensitivity for treaty relevant nuclides. And the 24 hours gamma spec sample. So the whole process takes 72 hours. And of course, the plume first has to arrive at the station from a possible release. So nothing too special here. My point was that we do report activity at the time of the measurement, and we do report activity concentration at the time of the sampling. And we have there, on one hand, of course, we have the emission yields that go into the equations, and I'll show an example where the data, for example, could be improved. And then for the concentration, we need the air volume. That's not too complicated. It's just need a calibrated flow meter. But there's also a collection efficiency, which should, and we have done studies on that and done measurements. But in fact, for our calculations, we just set it to 1 with an uncertainty of 0. That sounds a bit bad, but in fact, it's not that critical. Reason is when it comes to the concentrations, they are important to get an estimate of the size of the release. But then when it comes to uncertainties, we have to take into account that for size of release, we also need to look at atmospheric modeling. Uncertainties, they are quite large. Here's an example. What you can see is a map centered on Antarctica, and then 2 upwards from there. I could say northwards, but everything is northwards from South Pole. So, so upwards there is a dot, which is our monitoring station. It's a small island on around 60 degrees south, labeled there with AUP7. And then you see the colored area in each picture. This is the possible source locations in a 1-hour interval, 1 day, 2 days, 3 days, 4 days, 5 days, 6 days prior to sampling. And of course, the further you go back in time, the larger the area becomes. But my point here was just to look at the color scale. The scale, you might just make out, is on a logarithmic scale. And if you look, for example, at day 5, so in the middle at the bottom, that's going from 4 different colors fairly close together. That's basically that's 4 orders of magnitude difference, depending where the actual source location was. And so, yeah, the concentrations are important, but the uncertainties are not. For concentrations, we really just need order of magnitude. What is important, though, where we need to be precise, is in the activities, because the activity ratios can be used to work out what kind of event it was. And so the precise ratios are really important. As I mentioned, we also need good nuclear data, and for many of the isotopes we monitor, that's the case. So this is the list of the 92 radioisotopes that we are looking for. A lot of fission products, of course, some activation products. And most cases, nuclear data is pretty good, reliable. But for example, here, yttrium-91, the emission yield of the main line is a 15% uncertainty. So this is from a efficiency test we've done, and you see by in all the labs. And the red bars are at 15%. which just happens to be our acceptance range. But you see while the laboratories agree pretty well with the reference value and with each other, the 15% uncertainty there makes the comparison not very meaningful. So there it would be good to get some improved data. So just to summarize, we're looking at fission activation products. We're doing that with high resolution gamma spec. So the calibration, of course, is straightforward. Gamma calibration standards and sampling geometry. So there, the challenge is more around the nuclide data for some cases. And then the more mundane issues around sample inhomogeneities or the sample geometry, how that relates to calibration. So now we're getting to the noble gas monitoring. And when the treaty was, when this part of the monitoring was discussed, we're looking at different options. Of course, we have argon, krypton, xenon. Argon is quite interesting because there's a high fission yield on calcium, but it's actually not that easy to measure. So we are not using it for our monitoring network, but it's being considered for the on-site inspection measurement. Krypton is not so good, has a really long half-life and high background in the atmosphere. So xenon is the noble gas with that's most suitable. So high fission yields. There's several isotopes with a half-life in a good range from hours to 12 days. And at least at the time when the first setting up the measurement capability, we assumed there was a low atmospheric background. And now we find that the background in many places is close to the levels that we like to measure. So again, for the design of the network, there's a consideration of the 1 kiloton explosion to be detected. And so there's the 4 nuclides that are of interest: xenon 131M, 133, 133M, and 135. There's half-lives between 9 hours and 12 days. Already mentioned, we want a minimum detectable concentration of 1 millibecquerel or better per cubic meter for xenon 133. And 25 years ago, there was no such system commercially available. And so these had to be developed specifically for treaty monitoring. Just to give a quick summary of the principle of the sampling for xenon, and all the systems that we have either used or have tested pretty much work on this basic principle. You have at least two process pipelines, just because the while one channel is sampling, the second one needs to recover and then swap over. There are several stages, usually some prefiltration to get rid of water vapor, maybe some CO2, of course dust. And then there's a range of absorption, desorption cycles on adsorbents, either activated charcoal or silver zeolite or similar materials with a high absorbance for xenon. And then the separate stages, which helps with the absorption-desorption cycle to purify the sample and also to further increase the concentration. Particular for important for the measurement in the end is to separate it from radon, as it's reactive and interferes with the measurement. And in the end, you have, of course, a reactivity measurement in a gas cell. It can be 1 or 2 or more detectors. This is just to show the 2 types of systems currently in use. Now they're now reasonably old, and we started replacing them with the next generation type of systems. Yeah, we have the rightmost because it's an upgrade option. We have some of those already installed, and the others will follow over the next years. It's a long program. This is just to show, of course, the different systems have different detection systems, but just for the purpose that in terms of the different geometries, so on the left-hand side is possibly the one that has the closest to 4-pi geometry, where there's a scintillator cell, a plastic scintillator inside large sodium iodide crystal. Others have like a well-type detector where the beta cell is inserted. And then there's one where we have a germanium detector with a PIPS silicon detector on top, which is more like a 2-pi, 2-pi solution. Sorry, 2-pi, 4-pi. For the challenges we have around calibration is that there is no xenon reference material to start with. If we use xenon gas sources, there's an unknown transfer efficiency. The systems have not been set up to have 100% transfer of a source into the counting cell. Of course, the short half-lives, we need to have processes where we can calibrate the systems deployed, and it's a global network. Sometimes the transport takes a long time. Of course, for the cases where we just have gamma spectrometry, it's easy. We can use a standard approach with a calibration source, with the appropriate low density. For beta gamma coincidence systems, we have, if there's a high resolution detector, so germanium, we can also use a gamma calibration source, and then add some xenon spikes for the beta calibration. Otherwise, we use an absolute calibration type of approach. For xenon, for the coincidence spectra, here shown some examples what you get from calibration. So we have on the horizontal axis, we have the beta energy, on the vertical axis, gamma energy, each case. And you see the 4 xenon isotopes, radon, so basically radon itself, of course, doesn't interfere. It's the lead-214 that does, and a background. Now, you can already see from just visually the different xenon isotopes, there is some interference in the signal. The radon or lead, of course, normally is far less intensity. This is a purpose of calibration type of measurement, but it needs to be monitored because it will interfere. For ease of use, I guess, but also for historical reasons, the standard analysis procedure is based on regions of interest, like this, in this beta gamma coincidence spectrum. And they're basically designed so that the essentially cover one of the main isotopes. So like number 1 there would be radon or lead-214, and so on. And the calculation then based on a so-called net counting algorithm. So there's no peak shape fitting involved. Just to very briefly go through the different isotopes and what we have: the xenon-131M, predominantly a highly converted decay. And so you can have detected based on this conversion electron plus X-ray interference, which gives a strong signal. If you go just for purely gamma and blue there, you can see this very weak transition at 164 keV. Xenon-133, you can use the beta decay plus the 80 keV gamma ray, which is the second line from the bottom, what we would look at. And 133M, also highly converted decay, a slightly different energy from 131M. So you can distinguish the two conversion electron peaks, but of course it decays to 133, so we always have those two spectra convoluted. And 135, on one hand you have a strong gamma emission at 250 keV, which is in coincidence with beta decay, and at about 1 MeV. So that's an easy one to detect. For the absolute calibration, as you know, we have three unknowns and 3 equations to work with. So we can don't actually need to know the activity of the sample, but of course the assumption here is that the coincidence efficiency is given by the product of the two singles efficiencies, which are only really true if there's no spatial correlation. Now, as I've pointed out earlier, our detectors are not necessarily 4 pi, but it looks like the xenon isotopes have a fairly fairly well behaved, and there's not a lot of correlation between the spatial correlation between beta gamma emissions. So it mostly works, but we can only compare it against gamma spectrometry. And of course, we need to know the branching ratios and make sure we do that part of the calculation correctly, or we are in trouble. So for that, it would be really helpful to have some additional comparisons. So for noble gas, again, of course, we need to determine activity and activity concentration. In this case, actually, one point here was only to look at the volume. Now, we do not use the volume, even if we do measure it, the air volume. We have here the process efficiency, and the process efficiency is calculated based on the amount of xenon that was collected and a known concentration of the stable xenon in air. And that allows you to get rid of the volume and just use the measured volume. It's constant, which is, though, goes back to a single publication from 1956, where they worked out krypton and xenon contents in the air. So again, we do not need to be very precise for the concentration. But if someone is really interested, that would be a nice little project to determine what the xenon concentration in the air is and whether there's any variation and what's the what is the change with altitude, for example. So to support our calibration program, we have a QC program. This works by, we have a reference lab. Reference lab can certify a reference sample based on gamma spectrometry. And they can give us 2, 3, or 4 isotope combinations, depending what we want to do. And so we get certified activities and certified activity ratios out of that. Now this is a sealed vial, which we take to the system anywhere on the planet, and then inject it into the system. So this transfer efficiency is unknown. So we cannot use the certified activities, only the ratios we can use. The system measures the activity concentrations and measures the xenon volume. It's sampling, normally the environmental air. Of course, the concentration, the activities that we spike with are sufficiently high so that any possible presence of xenon isotopes would not matter. The systems have been set up that after the measurement at the site, the sample is transferred into a bottle, stainless steel transfer bottle, which can be detached and then sent to laboratory. So they get shipped there. The laboratory conducts another measurement. By that time, there's usually just 2 isotopes left, the long-lived ones, 133 and 131M. And so they can calculate an activity concentration based on the sampling date and compare it directly with the result from the system. We also get the xenon volume, which is not necessarily 100% of the sample measured, but it gives us a good indication on the performance of the stable xenon measurement in the system. Then we also test the laboratory's performance. We use a different reference lab there, Idaho National Lab. They prepare reference samples with Becquerel kind of activities that are sent to our laboratories. It's a small exercise, though. We only have a total of 9 laboratories participating. So, as I mentioned, these samples are becquerels. Normal atmospheric samples are millibecquerels. So it's quite different from the activities that are normally used for standardization at NMIs. But what we would like to see happening at a regular basis is a kind of comparison, not the same comparison that you normally talk about with NMIs, but to have Idaho National Lab provide a high activity sample for measurement at an NMI, and then would give us an additional support of the traceability at the moment, which is only done through gamma spectrometry. So here we have, for the xenon isotopes, we have 2 different methods. One is the high resolution gamma spectrometry, and then this beta gamma coincidence with different calibration methods. But ultimately, all calibrations, traceability is only issued through gamma spectrometry. And we only have a limited number of laboratories with the capability, and their capabilities are only at becquerel level. So having a link to NMIs would be really, really helpful. And summary for the aerosol sampling, the gamma emitting nuclides, we have a pretty good space. It's just some nuclide data could be improved. For xenon isotopes, there's no primary standard, there's no reference material, and we achieved the traceability through gamma spectrometry only. So for that, it would be good to develop or revive the gas measurement capability at LMIs. And then also, as I mentioned, have this stable xenon air reference redone would be nice to have, but it's not that critical. And with that, come to an end. Thank you very much.